calculate the molar solubility for iron 3 oxide, given its KSP value, in pure water and then also in a solution that has been buffered to pH 6.00. Hopefully you recognize that when given a pH value, this is going to allow us to calculate the hydroxide concentration, hydroxide being the common ion in this problem. So let's write the dissolution reaction, or the KSP reaction, for iron 3 hydroxide. Iron 3 hydroxide solid will form iron 3 ion and 3 hydroxide ions. The KSP expression then will simply be equal to iron concentration multiplied by hydroxide concentration cubed. We know that the iron concentration in pure water will be equal to the molar solubility, and in pure water the hydroxide concentration will be equal to 3 times the molar solubility. So we can use this expression to solve for the molar solubility in pure water. We end up getting 27s to the 4th. Rearranging that equation to solve for molar solubility, given the KSP value of 4.0 times 10 to the negative 38, gives us a molar solubility of 1.96 times 10 to the negative 10. So for part B, to determine the molar solubility in a solution that is buffered to pH 6.0, we need to use that pH in order to solve for our initial hydroxide concentration. The initial hydroxide concentration will be equal to Kw divided by the hydronium concentration. In pH 6, the hydronium concentration is 1 times 10 to the negative 6. We divide that into our Kw value, we get a hydroxide concentration of 1.0 times 10 to the negative 8. So our hydroxide concentration, final hydroxide concentration, can be determined using an ice table. Here, for this particular equilibrium, we can express the initial iron concentration as 0. Then when the equilibrium occurs, it will increase to S. The initial hydroxide concentration will be 1.0 times 10 to the negative 8 coming from the buffer solution. When this equilibrium occurs, it'll be plus 3s, and we'll end up with 1.0 times 10 to the negative 8 plus 3s for our final hydroxide concentration, and just S for our final iron 3 plus concentration. Then what we will do is take our concentrations and plug them into the KSP expression, and the assumption that we will make is the change in concentration of the common ion with respect to its initial concentration will be insignificant, so we can eliminate the 3s from this expression, and we'll get KSP is equal to S multiplied by 1.08 times 10 to the, 1.0 times 10 to the negative 8 cubed, allowing us to solve for S in a rather simple fashion, giving us S as 4.0 times 10 to the negative 14. Now it makes sense to validate that the equilibrium value for 3 times S is less than 1.0 times 10 to the negative 8, and it is, although this assumption will pretty much always work for this class. It is reasonable to validate it. So we'll see that the molar solubility also changed by several orders of magnitude, becoming much less due to the common ion effect.